Recording it.
Cool. So hey, yeah, I'm Patrick. I'm a TA for this course. Can you hear me? Yeah. And yeah, I'm going to present today's lecture on multilingual training and cross-lingual transfer. So, as mentioned before, there's a big disparity in the amount of data available for high resource languages when compared to low resource ones. And here we plot, I think this was plotted before, but the number of articles in Wikipedia for the top 100 languages. And I plotted them in log scale so you have a better notion of the amount of data. And as you can see, English has around 10 times more data than the 100 language. And this.
Are you sharing screen on Zoom?
Oh, yeah, you're right. Yeah. So as I was saying, English has about 10 times more data than the 100 language. And this doesn't even account for the other 6,000 languages that exist in the world. So we can expect to find basically zero data for those languages. And the problem is even worse for annotated data. For example, if you consider the case of bytext with English, so the number of sentences that have aligned sentences in English from the Flores corpus, we see that, again, the top language, which is Spanish, has around over 10,000 more sentence pairs than the bottom languages, which is Uzbekistan. And this is considering bytext with English. So one of the languages is a high resource language. And if you consider a language pair which only has low resource languages, such as Uzbekistan, Cabo Verdean, you can basically expect to find basically zero data. And so if you consider other NLP tasks, this problem will be probably the same. And this is a serious blocker for the development of NLP tools for low resource languages. So the main topic of this lecture is going to be precisely how to handle this lack of data by leveraging data from other languages. And we'll cover two main approaches, cross-lingual transfer and multilingual training. And we also cover some more extreme cases of data scarcity, zero-shot transfer, and some open problems in multilingual training. Cool. So to start, so the cross-lingual transfer framework is quite simple. The core assumption is that the information encoded in a trained model for one high resource language is useful for training a model in a low resource language or language pair. And so to do this, we first train a model on a high resource language and then use the weights learned by this model as an initialization for the model that's going to be trained on a low resource language. And for this to work, you have to make a couple of assumptions, which is generally you want your high resource language to be somewhat similar to your low resource language. You can think of if they're completely different, it's hard to believe that the information encoded by the weights of the parent model will be used for the student because the languages have nothing in common. And the other assumption is that the amount of data used to train the parents should be higher than the amount of data used to train the low resource language. And this is because you want that model to be good. And even if the languages are similar, if your parent model is not that good, you are not expecting the information to be useful to train a low resource language. But yeah, if in general these two criteria are respected, cross-lingual transfer can be quite effective. And I think in the original paper, they had improvements of over 5 blue points for all the low resource language pairs considered. However, the problem with cross-lingual transfer is that supporting even a moderately large number of languages is problematic. So consider the case where we want an empty system that supports these 4 languages in all directions, except the self pair. And to do so, you require 12 empty models. And in general, empty requires O(n) squared number of models per n language considered, which can become quite troublesome for a large number of languages. So if you consider, for example, Google or any other provider that supports over 100 languages, if they only used bilingual models, they would have to have over 10,000 models. And they tend to be quite big. And even for NLP tasks that normally only handle a single language at a time, while the overhead is only linear on the number of models, it can still be quite problematic if you have to keep 100 birds or 200 birds for every language you consider. So one way to go around this problem is to consider multilingual training. And multilingual training avoids this problem by training a single model that supports all the languages considered. To do so, we simply combine all the data, either through like simple concatenation or to some more complex mixing procedures, which we'll cover a bit later. And then you train the model on this mixed data. And the assumption behind multilingual training is very similar to the one in cross-lingual transfer, which is that during optimization, the information that the model is learning to learn a language is useful to learn the other languages as well. And it effectively boosts the performance in most of, at least the low resource languages considered. It also makes another important assumption, which is that the model has enough capacity to learn how to deal with all the languages. And this assumption seems important because these models tend to benefit a lot more from scale than bilingual models. So it seems that capacity is important for this to work. And in general, for certain applications and tasks, you might have to do some tricks. For example, since here, if you just feed it, how are you? And the model wouldn't know which language it wants to translate to because it's a many-to-many model. So in this case, what you do is just you prepend a tag representing the language that you want to translate to. So if you want to French, you just say to French, how are you? And but yeah, these are small tricks. And for example, you don't even have to specify the language of the source because the model learns automatically to do language identification because it's part of its task. And for other tasks that just consider single languages, in general, you don't have to do these tricks and it will just work straight out of the box. And yeah, this framework works quite well straight out of the box with some caveats that we'll explore later. And yeah, these are basically the two main paradigms for multilingual methods. But let's say now that you want to train a good model for a new language. Let's say you're considering, you decided that now you want to, serve a new language in production. Or another use case, consider the COVID-19 response. 2 years ago, go ahead.
Does it even learn what the source language is, or does it even care? Why should it even learn that?
I mean, we don't know if he explicitly learns the source language. I assume knowing the source language is useful to do translation. But I wouldn't say learns it explicitly. May learn it some form of implicitly language identification.
But is it even doing that in that case?
In this case,
yeah. Like why would it even try to do that?
Because assuming that the model needs to understand some form of English, it needs to know that the language that's encoding is English.
Well, also in this case, all of the source languages are English.
Oh.
Yeah, I would consider, this is simplified because consider this case here where it could be how are you, or in Portuguese, como tu estás. In this case, the model needs to somehow understand the language in the source because it needs to know which language to translate from. And in that case, you can ask, oh, is it learning? I would say yes, but I don't know if there's research on probing language identification in these models. Does that make sense? Cool. Yeah. So going back, consider the COVID-19 response. 2 years ago, new information about COVID was coming out basically every day. And I assume most of you already knew English or maybe some other popular language. So you had access to this information. You just either directly got it from the English source or through a high quality MT system. But this was not the case for many peoples in communities that were affected by COVID, but that didn't have computational resources for the languages. And these communities would still benefit from having this information. So this was a perfect use case for MT systems that quickly adapt to new languages. And there was even a research initiative led by universities and in industry. I think, Graham, you were on it, right? Yeah. And to precisely get resources for future cases where we might need quickly adapt to new languages. So yeah, so how do we do this? How do we quickly adapt to new languages? And one approach proposed by this paper to quickly adapt to new language is to directly combine cross-lingual transfer with multilingual training. And what you do is simple. You first do multilingual training on many languages. I think they did 58 languages in the original paper. And then you just fine-tune your model on the new low resource language you're considering. And again, the assumption here is a mixture of the previous two assumptions, which is the multilingual parent model will have even more useful information in its weights to initialize the new model than a bilingual model would have. Because the assumption is that a multilingual model needs to generically learn languages in a way that a bilingual model doesn't have to. And so you would expect this information to be useful to adapt quickly to a new language. This paper also proposed another cool method to further improve the transfer, a regularized fine-tuning. And the idea is simple. You fine-tune on a low resource language, but at the same time, you also fine-tune with a related high resource language. And the idea is that this regularizes the models and prevents overfitting to the low resource language if that language has relatively low amounts of data. And yeah, it seems that this cross-lingual transfer from multilingual models generally outperforms cross-lingual transfer from bilingual models. And importantly, not only with better final performance, but converging much faster. And secondly, it seems that regularized fine-tuning is important to avoid overfitting. And And just as a caveat, this is an idea maybe to try to homework too, because when you fine tune Flores, you only fine tune on the low resource language, but maybe something to try would be to do this regularized fine tuning. Just an idea. Maybe this is a time for questions. No? Cool. Feel free to stop me anytime. Okay, so let's take this to the extreme. Let's say we have no data for the language or language pair of interest. Can we somehow still get a model that works on this by leveraging multilingual training? This is generally known as zero-shot transfer. And at the beginning, you might think no, but let's consider the case in NMT. In general, machine translation data is very English-centric. And let's say we want a system that is able to translate Zulu, Italian, and English in all directions, let's say. You could probably find very easily data for Italian and English. Just go Aeroporl, like literally anywhere you find it. But for Zulu English, you might find some Bible data. It's still some data, maybe not as much as Italian English, but you're probably not very likely going to find Zulu Italian parallel data. But we still want our system to translate between Zulu and Italian and the reverse. So how do you go about this? Turns out the answer is quite simple. And the naive approach of training our model on the language pairs that we have data and testing on unseen language pairs just kind of works out of the box. So in this case, you train it on Zulu English, Italian English, English Italian. And at test time, you'd feed it Zulu, but you'd give it the tag Italian, which is a combination that the model has never seen in training. But despite this, the model sometimes, not always, will still be able to translate to Italian. Which is kind of surprising because the first time I heard about this, this was a cool thing about multilingual models. But there are some caveats. In general, the performance is not always the best, as you would expect. So another thing you can do is, if you have access to unlabeled data, which is a fair assumption, monolingual or unlabeled data tends to be more abundant than labeled data. If you had access to the data, what else could you do to improve performance? And what you can do is add a self-supervision or denoising objective to your model. So in this case, if you had Italian data, monolingual data, what you could do is, for example, you could mask your data like birds and ask the model to predict the masked words. Or you could, for example, just pass a prefix and ask the model to auto-regressively decode the rest of the sentence. Any general true and tested denoising objective would probably work. And if you did this, in general, research has shown that this normally tends to help performance on zero-shot transfer. And I think this is similar to an approach discussed by Graham in the data augmentation class. Yeah, another way to improve your zero-shot transfer in NMT is by aligning representations. So one hypothesis for why zero-shot multilingual models works at all is because the encoder learns language invariant representations. So let's say you have a sentence A and B, so they're the same semantic content, but in two different languages. This hypothesis says that when passed through the encoder, the representations will be probably similar. And however, the multilingual objective doesn't explicitly enforce this. So all we're doing is just training our model on the mix of data, and we're assuming that this happens, but there's no explicit enforcement of this. And so one potential approach proposed by this paper is to actually just explicitly enforce this. And the way they do it in this paper is they pass two sentences in two different languages, the same sentence in two different languages to the model. They get the representations from the encoder, and then they have some alignment loss, which just says how similar the representations are. And you have this extra term in the loss. And in their paper, they show that this massively helps to boost performance to zero-shot transfer, which is expected because if the model does learn language invariant representations, then it should be easy to transfer from new language pairs that the model has never seen. And yeah, another point, just to move a bit outside of MT, is that zero-shot transfer also works for pre-trained language models in the standard pre-trained and fine-tuned paradigm. Concretely, if you had like an MLM model such as MBERT that was pre-trained on a large monolingual corpora from many languages, and then you have a downstream task that you want, and you just have labeled data for one language, if you fine-tune your model on that language, it's quite likely that at test time, if you want to test on the same task but on a different language, the model will still work. And this is like zero-shot transfer for language models. And the reason that this works is that multilingual models seem to also learn, or multilingual language models seem to also learn language invariant representations. For example, some could argue that these models maybe are able to do zero-shot transfer due to some vocabulary overlap. Let's say French and English, maybe it works because some of the words are shared between the vocabularies, and that's not why it works. But that doesn't seem to be the case. And in this graph, you see a plot where on the x-axis is the amount of overlap with English, and on the y-axis is the performance. And you see that even for languages that have generally very little overlap with English, still are able to get quite good zero-shot performance. So it seems that the model it's not particularly about. Go ahead.
When we fine-tune for the downstream parts,
Yeah.
so does the language has to be one from the one?
Yes. I think, at least from what I know, yes. Because you would expect the model to be able to learn language invariant representations, but you'll only be able to learn it for languages that I had seen in the pre-trained corpora. And this is something even for MT where there's some research that tries to go around it, but even zero-shot for MT normally still considers only language that at least have been in one language pair. There are some research that tries to scale this beyond this, but in general, this normally works mostly if at least the language is one of the language pairs that the model has been trained on.
But if it's very similar to
Yeah.
another language that you saw at training time, it can work. And also, if you continue like training as a language model, you can do. I mean, it's always easy to do better than really, really bad.
Yeah.
You know, like if you're going from like 10% to 40% accuracy, you can manage to do that. But if you don't have any data in your pre-trained model, it's hard to get, like really good accuracy unless it's very similar to another model that's in the pre-trained model.
Yeah. So for example,
Another language.
what you could do here is like, if you consider this, where is it? Sorry, if you consider this framework, maybe you could use some kind of this where the language is not actually part of your original language in the language pairs that you consider. And it could work, but in general, it's not very good. In the paper that we're gonna discuss, they try to go a bit beyond this, but in general, it's better if the languages are already in the original training set.
Yeah, but I was shocked in the paper that Patrick just talked about when we trained on 58 languages and then just applied the MT model to Catalan, I think, or Galician, which is it's a language that's kind of like a dialect of Spanish or Portuguese or something like this, but still pretty different. And it got a blue score of 13, which is actually not non-trivial. So if the language is very, very similar to something else you've seen before, you can actually do pretty well, even for a really difficult task like MT. And for something like tasks, also one important thing to know, I'll stand up. One important thing to know is that tasks vary a lot in their difficulty. So tasks that are going from language to doing like classification or part of speech tagging or named entity recognition or something are going from a very large label space down to a small label space. So those ones are relatively easy. Machine translation into English, for example, or into another language that's in your training data is much easier than machine translation into the low resource language because
we're gonna cover that in the class.
Okay. So and
no spoiler.
Sorry. Patrick will cover that. So basically, like the answer, there's a lot of nuance in the answer to that question.
Go ahead.
The script has to exist in the pre-training phase for it to work.
Yeah, because it needs to have symbols like BP symbols for it. So it needs to exist. But again, at test time, the script doesn't have to be the same that it was fine-tuned on. For example, you can fine-tune on English, have some other language with a different script that was on the pre-trained corpora, and it will still work, as you see from this vocabulary overlap graph, basically.
What is the graph trying to tell us?
So the graph is trying to tell you that, like, even for languages that have very little vocabulary overlap, so the left side, right, you're still able to do zero-shot performance. If you look at the blue dots, you're still able to do relatively good zero-shot performance, even if they share basically no vocabulary.
Are those plotted for the same vocabulary, the English words?
Yeah, this is like the languages there are languages and the overlap is compared to the English vocabulary. Let's say like if you're considering like Italian, a point there which represents Italian would be the x-axis would be how much Italian shares vocabulary with English, basically.
But aren't those two different models, English BERT and multilingual?
Yes. So
Should we be even?
so the English BERT just shows that like if it doesn't share any vocabulary, it doesn't work, right? Because English BERT was not pre-trained on many languages.
But multilingual BERT already has English in it, right?
Yeah.
So those English embeddings will also be different than the English BERT embeddings, I'm guessing, because that's a different.
Yeah, but in this case, you're not even comparing embeddings. You're just comparing literally the raw vocabulary. So you can measure a vocabulary based on the corpus. This is not about the embeddings themselves. It's just saying if the language has a vocabulary, which you can measure without going to embeddings.
Okay. Okay, I'm sorry. I thought they were the plot of the embeddings.
No.
Oh, okay. That is both. Okay.
What's the y-axis of that plot?
It's the zero-shot performance, basically.
But it's not.
It's F1 score. I think this is accuracy or like some classification task, basically. Yeah. So it's F1, which is like accuracy and recall, basically. Yeah.
When you're measuring vocabulary overlap, do you look for exact matches of strings, or do you look for, okay, these two languages both have a word for automobile or something like that?
I don't recall what they did in this paper exactly. Maybe I'm not exactly sure. I would assume they went for the simplest option. Maybe just went straight up word overlap, whole word overlap. But yeah, I think the conclusion is that they're just trying to show here that like it's not about the vocabulary itself or like string matching. It's about the representation being invariant in general. But yeah, I don't know exactly the answer to the question. Yeah.
When you say like zero-shot transfer, the models have still seen the new language.
Yeah. It's a definition problem. It's zero shot in the sense of fine tuning.
Okay.
It's not zero shot because the language exists in the pre-training, and it's the same way that the zero shot for MT can still be caveat because it's zero shot, but in general you consider that the languages were individual at least in one of the language pairs before. But yeah, to answer your question, in this case, yeah, the language was in the pre-training, but you still call it zero shot. Yeah.
I have another question about how is like words in different languages represented.
Okay.
Like say if you have a homograph of languages, but they just say
Yes, they will be the same token. If they're exactly represented with the same string, nothing else, they will be represented as the same ID, the same token. Yeah. Any more questions? Maybe it's okay. One last one.
Like, could you explain the intuition behind why the alignment auxiliary class includes?
If you want to explain the intuition, the intuition here is imagine you have, let's say the Zulu and Italian example before. You train your model to predict from Zulu to English, right? Your goal is that like, if the representations are aligned, it doesn't really matter for the model which language you asked it to translate to, right? Because it could have come from any language, but the representation is going to be the same. So you expect it to, if the representations are very well aligned, you can do zero shot for any of the, if you have the space of n square combinations, if there's some pair there that you didn't consider, if the representations are perfectly aligned, then this will generalize basically to every pair that didn't have training data, basically. Does this intuition make sense? Because
after the power pass, the hidden representation is like you have like a distance metric that you're using.
yeah, what they use in this paper is like if you have embeddings for each token, they pull them with mean or something like that, and then they use like some distance measure between one language and the other, and they try to minimize it basically. They probably have to do some tricks to get it to work, but this is the basic idea. Yeah.
And it's like the idea of an interlingual before, right? So if you take inputs from different languages and encode them into a representation that's the same, regardless of which language it was in, it moves you closer to an interlingual, which should generalize in like any translation.
Yeah. Basically, if they're perfectly aligned, after the encoder, you don't care which language it came from, basically. That make sense? Yeah. Cool. I'll try to move on. Just to complete on this, while it does work for languages with low overlap, they found that like for typological different languages, so languages with different typological features such as subject-verb ordering, this doesn't generalize as well. So it seems that like they're universal, but up to a certain point. And maybe with more scale and more powerful models, they'll generalize to typological different languages. But in this particular case, that doesn't seem to be the case. So there are some caveats with this. Cool. Okay. However, not all is perfect, and there are problems with these frameworks. consider the problem of scaling like an MT model to over 100 languages. So this is normally called massively multilingual MT. So the first issue you're going to run into is that your training data is going to be highly imbalanced. So high resource languages, as you've seen before, have way more data than low resource ones. And if you just naively train on this, your model might not learn to translate from the low resource languages at all. It just might completely ignore it. Because if you have 10 times more data from one language pair, like the model will, in terms of loss, will just under-prioritize this. So it's important to upsample your low resource data in this setting. So you want your low resource data to appear more than it appears in frequency counts on the corpus. How? So one way is if you consider sampling from the data as getting data from the corpus as a probabilistic process, you consider sampling based on the data set size for the language pair, and you can scale that sampling by temperature term. And for example, if you have temperature 1, you just sample proportionally to the original corpus size. If you have a very high temperature, you'd sample uniformly from all the language pairs. What you want in this case is something in the middle, because as I said, if you do temperature 1, you're probably going to have a model that doesn't learn at all to translate the low resource. If you have a very high temperature, your model is probably going to lose not only a lot of performance on the high resource, but might not even learn the low resource because it cannot leverage information from the high resource language as well. So you want something in the middle. But yeah, overall, this is a very heuristic-based process. Normally, you set a temperature, train, check the performance on the validation set, change the temperature. But there are some approaches to try to do this automatically. For example, in this paper, they try to directly optimize the sampling procedure. So they consider that they have a parameterized data mixer, let's call it data mixer, which has some parameter, for example, the temperature. And what you do is you have a temperature, you train your model for n steps, you measure the performance of your model on the validation set. And based on the performance on the validation set across all the different languages, you can take the gradient with respect to the data mixer. And you can do this either through like reinforcement learning, or you can do it by explicitly optimizing with meta learning. And if you do this, you can have a gradient that will move the data mixer towards something that improves the performance on the validation set. Again, this is highly non-trivial. Meta learning and reinforcement learning are kind of tricky, but this just shows that like sometimes you can make it work automatically without having to worry about manually setting the data sampling. But yeah, overall, this is not a closed problem. It's still an open problem.
What is the rationale behind using meta learning? It's like meta learning is really learning to learn, like in classification problems, say like the algorithm will learn to do say 5-way classifications, and then for a it will do the 5-way classification. But here, what's the point of using a meta learning?
So meta learning is not only that. That was the original scope that meta learning was introduced. But so let's not call it meta learning. Let's call it second order differentiation, if you prefer, which is basically the same. And what you're doing is you're getting the gradients with respect to your scorer, which requires a second order differentiation, and you're doing that to update the scorer. I call it meta learning because it's simpler, but like what you're doing here is either reinforcement learning to get an update on your scorer, or second order differentiation to get an update on your scorer. And what you're trying is learning a scorer that helps the model learn better. Does that make sense? Meta learning is a bit fuzzy sometimes.
I'm gonna disagree with Patrick and say meta learning is not fuzzy, and this is definitely meta learning. But basically, meta learning is learning something that you use at training time and then throw away at test time. And here, basically, what you're doing is you're learning to which data you're going to use, or which balancing of data you're going to use to optimize the performance of on the language or languages that you're interested in. So I think basically the reason why you would want to do this is because you're going to want the balance. You're going to want to optimize the performance on a particular target, be it like all of the languages or a particular language. But what I want to say is meta learning, like a lot of people use meta learning in a fuzzy way, but that's my particular definition that I'd like everybody to try to use.
If it makes you more comfortable, you can call it second order differentiation.
So what's the intuition behind using similar upweighting with similar gradients? So what does that do with respect to like the multilingual dataset?
So the intuition I have bit, I think that what they're trying to say here is that like, you want the gradients. Wait, language have a similar gradient. I don't remember what I did when I wrote this. The intuition that I can give you here is that like, you don't have to think about the direction here. Like you just think about the simple operation, which is if you consider the validation loss as your objective that you're trying to optimize, right? What you do is if you differentiate through this validation loss with respect to the scorer, you're gonna get a gradient, right? With respect to those parameters. And this gradient tells you where to move to improve the performance of your model, of your empty model on the dev set. And I think maybe that's what I meant by that line, maybe. Wrote it quite late at night. But the idea here is that like this gradient, this meta gradient, it's something that points towards the direction that the scorer in the scorer that will lead to an empty model that's better on the validation set, and that's why they call it the multilingual dev set. And the way you weight them on the multilingual set will change the weighting. So if you consider every language the same, right, this will learn a weighting scheme on the scorer that overall gets an average performance on all the languages equally well. Does that make sense?
Yeah, and also just to give an example, like what Patrick said is right, but just to give an example, like let's say there were lots of Indo-European languages in your dev set and not very many languages like Chinese in your dev set, but Chinese had a very large training set.
Yeah.
The average gradient of the dev set, if you took the same number of data from all of the languages, would look like more Indo-European, basically. The gradient update would look more Indo-European, which would mean that the gradients from the Indo-European languages would be more similar. And so the Indo-European languages would be upweighted during training, and Chinese might be downweighted because its gradient was less similar to the dev set. So it's basically like, it's identifying which languages look like all the average of the languages in the dev set, or actually it's measuring each language individually and then taking the average of the similarities.
But yeah, this is flexible. If you wanted some language in a dev set that you want to prioritize in terms of performance, you could just upweight it on the validation loss, and your score will learn to what's the optimal temperature parameter to get that particular language to be better. So this is flexible enough. But I think in this case, I consider every language is worth the same in some sense. Cool. Go ahead. No, this is just like problems with multilingual training. And in this particular problem is like how to balance your data, basically, because you're going to have data from many languages. Make sense? But it has implications for zero shot, because the better your multilingual model is, the better zero shot performance you're going to get. Make sense? Cool. So another problem you're going to run into is multilingual vocabulary construction. So the way you currently do it is probably not optimal. So as previously discussed, normally what you do is you could just concatenate all your data and learn a BP model over this concatenated corpora. But this will probably over-segment your low-resource data, because the way the statistical model works is that the more you see a particular subword, the more likely you will be to be an actual subword unit. And because there's so little data for the low-resource languages, those are probably going to end up with just being sequences of characters. And a standard approach then is to do the same we do with data, which is just to, with data selection, which is just to upsample the low-resource languages when building the BP encodings. However, as you scale to more languages, if you have a fixed vocabulary, it's inevitable that you're going to end up with languages that are over-segmented. Because unless you scale linearly the amount of vocabulary with the number of languages, you're always going to have a problem where there's vocabulary and there's not enough tokens to represent that vocabulary. And so it's not clear currently what's the best way to solve this. So I'm just going to discuss something that like I'm not saying you guys try this, but it's an approach. It's like character level language models. So one approach to not worry about VPs is not to have VPs. And character level models had their ups and downs in NLP. But with the advent of deep learning, they mostly started lagging behind. But recently, there's been some papers that have tried to bring them back. So this is a paper called Canine. And what they do is, they just consider characters and they have a bunch of tricks like hash embeddings, and they have a downsampling to reduce the complexity, because one of the problems with character embeddings is that because you have more tokens, it's more computationally expensive. And so here they do a bunch of tricks. And it seems to work for the particular task they tried, which is tidy QA. And there's also another paper called by T5, which tries to do something very similar to T5, and they also seem to get decent performance. However, I do want to point out in general, with the evidence that we have right now, they're still subpar compared to subword models. So if you're trying to get the best model you want, I'll still advise you to use subwords. I just wanted to point out that there is work trying to go beyond subwords because of this problem with subword units. And it's starting to maybe get closer, but I would say it's still not that close. That's my opinion, at least.
Which might mean it's a good project.
Yeah, if you get it to work. Now, if you get it not to work and you explain why, that's a good project as well. Cool. So the other, and I think that's the larger problem, is that at least in MT, the case that we're analyzing, sometimes these models, these multilingual, still underperforms bilingual models. And what I'm showing here is on both graphs, we have the difference with the baseline, which is the horizontal line, the bilingual baseline. And from the left, high resource, from the right, low resource, and with different number of languages in the model. And what you can see is that, like, even though for maybe for the low resource languages, performance, you gain performance, generally for high resource languages, you'll lose performance. And if your goal is to have a single model for everything, this is bad, because probably going to be serving those high resource languages more anyway. And this is particularly bad for the one-to-many setting. So the case where you have a single language, you're decoding to many languages. Because as you can see, for the any to English, at least the low resource languages have much better performance than the bilingual model. But on the English to any, even that is questionable at some point. So there seems to be a case where it underperforms bilingual models, and the one-to-many setting is much harder. So there are multiple hypotheses for this phenomenon. So one is that there's a negative transfer in learning between the languages. Recall that the main benefit of multilingual training is the transfer of information between languages that helps each other learn that specific language. However, the opposite can also happen. It can happen that certain information learned from a language is not useful at all to learn another language, and due to limited capacity, is actually harmful to learn another language. And so we want to mitigate this negative transfer so that we get the maximum performance in all the languages considered. And one way to circumvent this problem is to just add a small language-specific module or adapters, what they're normally called, to your model. And this would be, dynamically added depending on the language you're considering. And the intuition here is that, like, these language-specific models can learn the language-specific information needed to learn to do the translation task, while not negatively interfering with the general parameters shared by all of the languages that live outside the adapter. And again, this is an hypothesis, but the results seem to show that when you add adapters, the models are much better at matching bilingual baselines. So it seems that their hypothesis might be somewhat true. So yeah, this is a cool approach if you're trying to do low resource adaptation of general pre-trained models. It's quite hot right now. But yeah, the second problem is that language generation, and the second hypothesis for what we saw before is that language generation and decoding is inherently harder than encoding. And Graham already mentioned this. So recall that the task of the encoder is to map a sequence of tokens to distributional representations. And the decoder is the opposite. And there's evidence that the latter is a harder task. So for example, if you leverage monolingual data through self-supervision, it seems that it's more beneficial to use it on the source side than it is to use it on the target side. This is to say, if you have monolingual source data and you use self-supervision, you're probably going to boost your zero-shot performance way more than if you had monolingual data on the target side and you did self-supervision on that. So it seems that it's more helpful to have this self-supervision objectives on the source side. And the second is that synthetic data is more effective if the target side is natural than if the source side is natural. How to describe this? If you have a monolingual data, source monolingual data, right? And you forward translate it, which is like the reverse of back translation. And you have plenty of this data and you try to scale your model, there's going to be a point that that data is not beneficial anymore. And the unnaturalness of the target side, which also happens in this case, is that the source is going to be natural, but the target is going to be non-natural. And this unnaturalness of the target side prevents the model from improving. While if you have the opposite, you have target side natural data, and you do back translation, it seems that you can keep scaling your model because the model still benefits from this back translation data. So it cares more about the fact that the target side that is natural, then the source side data is natural. And to me, this is a hint that like the decoding or generation procedure is much harder than the encoding, according to my intuition in this data. And nevertheless, data augmentation seems to work. And the best thing we got at the moment is to do back translation, which seems to kind of work to improve the decoding procedure.
So when you say back translation here, what you're saying really is from target to source. You're not talking source to target.
This is source to target is the forward translation. And the back translation is you have a reverse model and you take target side multilingual data and you do pseudo source data basically. And that seems to be much more helpful than doing the opposite. And that might explain why all the papers that we see use back translation and don't use forward translation basically. Cool.
I have a trivial question, but in all of the cases models which use back translation, do they share the same parameters with the forward translation one?
No, generally no. I think there's work that's tried to do this, but generally you have a separate model that does the back translation, unless you're considering, I don't know the word, bidirectional. There's like a particular problem of doing precisely translation on both directions. But in general, if you're doing just bilingual translation, you just create a separate model. And normally you do it on clean data in particular. Okay. But overall, if you combine all our best tricks, such as self-supervision for source data and back translation for target monolingual data, and we scale our models, they seem to be able to compete with bilingual models. This is for comparison with the other paper, because the other paper was 2018, 17. This is like recently from 2021. And in 2021, for the first time, a massive multilingual model from Facebook was able to beat almost all the bilingual models on the WMT share task, which is the most popular machine translation conference share task. There is a caveat that if you were to fine-tune that model on a particular language pairs, maybe that model would be even better. It would be a bilingual model that's better. And maybe you're right, but I still think that this is like a big accomplishment that a general multilingual model was able to beat all the specifically fine-tuned bilingual models. That was mine, sorry. And if I recall correctly, they didn't even use that much of the tricks that we described before. They didn't use align representations or anything like that. So this is another example of the bitter lesson where scale basically won, and they just have a lot of data to train their models on, and their multilingual model just scaled well with it. Okay, finally, the last problem, how to do evaluation. So we have this massive multilingual model, and if you go back, oh, there's a bunch of like blue improvements there, great. But how do we compare all of this? Let's say you're considering blue. How do you choose between a model that has 40 on English, French, and 15 on English Zulu versus a model that has 35 on English, French, and 20 of Zulu? It's not clear because, you know, it depends on what you care about. And even if you consider you don't have this problem, what does it mean for a language to have +5 blue compared to another language? Is it as beneficial to have +5 blue points on French versus Zulu, or is blue more representative of quality, or it has a better, like, how do I say it? Smaller improvements represent more improvement in quality than another language. And so it's not clear. This is, I think, one of the hardest problems that I described. Ultimately, I think this will depend on the end use case of your model, and it will depend on how you're going to use this model in real life. And the only way to say is that overall, if your users are more satisfied overall over a whole population of users of your model, if they're more satisfied with your model, they're not. Because holistically looking at averages of depth sets is going to be always problematic, basically. And yeah, the discussion today is towards the next 1,000 languages, which is took all the concepts we described to the extreme. And yeah, you're going to have to tell us like an interesting experiment that we found and implications, or an experiment that you didn't see and you'd like to see, basically. Yeah. Any questions before I wrap up?
I'm sure this question has been asked a lot of times, but why are we still considering blue? Why aren't we talking about other metrics?
We are. It's just no one listens. Yeah. No, we talk. There's a whole share task about metrics. Basically, it's just how like this is like a community thing. Like it's an adoption thing. Even if everyone knows that there's another metric that's better, if people still use the other metric, like no one's going to eventually change. It needs to be a movement forward of everyone at the same time, or at least everyone individually start using that, such that people around you start using it as well. So for example, in Graham's lab, we try to mostly use another metric as well besides blue. But if we don't use blue, someone's going to complain that we didn't use blue. So I think the best way to go forward is to incorporate blue and another metric of choice, and hopefully in the future we move away from blue. But answer to your question is that like, it's hard to get the whole community to suddenly move from a previous metric to a new one, I think.
So the two problems that you described in the previous slide, those will be applicable for any metric that we take.
Yes, I would say it's even worse for the newer metrics. For example, I have a rough intuition of what +5 blue means. I have almost zero intuition what 0.1 comet means. Like so, but I think this is just an experience with the metric itself. We know blue well, and so we have an intuition what blue means. With comet we don't basically.
And one other comment is actually in the paper for the reading. If you looked at the results into other languages, blue is useless for comparing them. If you like looked at the graphs and stuff like this, it doesn't make any sense. But if you look at CAREF, it's actually pretty reasonable. So like, especially if you're looking at generation into other languages with varying morphology and stuff like that, I would almost say you need to report blue in your paper, unfortunately, because otherwise, if you don't,
you get rejected.
Well, reviewers will complain basically, but you could report it in an appendix and say, we don't think that blue is useful for comparing systems with different target languages. We included the results. In the appendix, but you know, we're going to look mainly at CURA.
But you're risking a lot if you do that. You're risking.
No. Yeah, that's fine. Not reporting them at all is not a problem, but it's.
Could you clarify why is it useless again?
Well, if you look, like it varies extremely widely, like depending on the language, and the reason why is because blue is very sensitive to the length of the words. So if you have a sentence with long words like Turkish and a sentence with short words like segmented Chinese or something like that, then for equivalent translation accuracies, Chinese is going to have a really high score. And actually, Chinese might not be the best example because it uses ideographs, but like, you know, English, for example, has relatively short words versus Turkish, which has very long words. So Turkish will have a much lower blue score, even if the translation quality is equivalent.
So this is the second point on this, basically.
Because you can't compare across languages, but you can compare a language with previous results for that language.
Yeah, generally, yes.
Mostly, also
Same data
blue
set.
is very sensitive to the length of the sentence, for example.
Yeah.
So very short things, it's easier to get a high blue than very long things.
But yeah, it's important the same data set. Blue is not directly comparable across data sets either.
So yeah, so basically, like if you're comparing generation into different languages, you know, I don't think blue is good to compare quality across languages.